Good afternoon and welcome back. So we're going to have our first short talk for today. Sandoel Vieira from UFPI who's going to talk about the difference on the minimum difference between the Markov and the Lagrange spectra, right? So welcome, thank you.
Okay, can you hear me? Yeah. Okay, so good afternoon, everybody. It's a pleasure to be here, right? First of all, I would like to thank the organizers for the invitation. And today we're going to talk about the infimum of this difference set between the Markov and the Lagrange spectrum, right? This is a joint work with Harold Arazo, Davi Lima, Carlos Mateus, and Carlos Gustavo Moreira. So before talk the spectrum themselves, let's give a bit of motivation of how these spectra arise from rational approximations of irrational numbers. In that sense, the first result is due to Dirichlet that he showed that for an alpha irrational number, this inequality here has infinitely many rational solutions, right? And a little bit after that, Markov and Hurwitz improved this result by putting here in the denominator up front a square root of 5 in such a way that they still proved that this inequality here also has infinitely many rational solutions. And in some sense, the square root of 5 is sharp in the sense that if you take alpha, the golden ratio here, this inequality with the square root of 5 plus epsilon here up front only have infinitely many rational solutions. So, well, you may ask, what about a specific alpha? We might be able to improve this constant k here up front in the denominator in such a way that this inequality also has infinitely many rational solutions. Well, in fact, this motivates this definition k of alpha as the best constant of Diophantine approximation of the rational alpha fixed as the supreme of the positive k in such a way that this inequality with k here, the denominator, also has infinitely many rational solutions. And, well, as we've just seen, k of alpha is at least square root of 5 for every alpha irrational. And as you see the previous result by Hurwitz, we also see that the k of the golden ratio is actually square root of 5. So we collect all these finite constants of best Diophantine approximation in a set and call this set the Lagrange spectrum, right? Okay. But today we're going to talk these spectra from a dynamical point of view given by Perron, right? And, well, if you call capital sigma the set of sequence of natural numbers and the small sigma the usual shift, if you define a function f like the sum of these two continued fractions here, so you define f here, like this, where this notation means this sum of continued fraction here. Well, and so on. Well, if in this setting, we can also view the Lagrange spectra as this set of finite lim sub of f along of the orbits of the shift map, right? And, well, in this setting, we can also define another interesting set that we call the Markov set as the supreme of f's, the value supremes of f along the orbits of the shift map as well. It's not so hard to see that L is a subset of M, and they are both closed subset of the real line, right? So before continuing, let's give some classical result about these spectra. The first one is due to Markov, and they showed that both spectra are equal up to 3. In fact, these spectrums, in this region, this spectrum is well described. It's a sequence of irrational numbers converging to 3, right? And a bit after that, how prove that if you define C4 like this set of continued fractions with symbols just between 1 and 4, we actually can prove that C4 plus C4 is an interval with length bigger than 1, and you can use that to prove that this half line from 6 to infinite is a subset of L, and as well is a subset of M. And Freiman proved that the biggest half line that you can put in the Lagrange spectra start in CF, where CF is this constant here. Okay, so more recently, Moreira proved that not this spectra have the same beginning and the same ending, but they actually have this kind of matching intermediate fractal structure, in the sense that if you look for the half dimension of the Markov spectrum, of the intersection of the Markov spectrum with the half line from minus infinity to 3, the half dimension of the Lagrange spectrum in the same portion of the line, are actually equal, and this function dt here is a continuous surjative function. Okay, so from what we just seen, these both spectra look like the same, but actually they are different sets. The difference between M and L are actually a non-empty set, and this set has a interesting fractal structure. The first result in this direction is due to Freiman and Flahav. They prove in the 16th and the 17th that these different sets actually contain two sequences of numbers converging to these two numbers here. And more recently, Matheus Moreira, along with Policotti and Vintinova, they give this upper and lower bound of the half dimension of this different set. So it's an interesting fractal set, right? And in that direction, we also have proved that, along with Lima and Matheus Moreira, that this different set is not a closed subset of R. Okay, although this previous result showed that the Lagrange and Markov spectra are not the same, we wonder whether the difference begins right after the point 3. In other words, is the infimum of M minus L equal to 3? Well, this question arose naturally in this work, where we construct a specific sequence converging to 3, and we are able to prove the four first numbers of this sequence are actually in M minus L, right? These 4 numbers look like this one here, right? But in that time, we were not able to prove that the whole sequence belongs to M minus L. Well, in this work, we actually proved that question. We answered that question positively, and we proved that for every epsilon positive, the Markov spectra and Lagrange spectra are different sets in this region from 3 to 3 plus epsilon. And consequently, you have the infimum between M minus L is actually 3. Well, we prove a little bit more than that. We give a below estimative of the half dimension of this different set between 3 and 3 plus epsilon by this expression here. Well, C0 is this constant here, and that capital W is the Lambert function, right? Well, but how to construct a point in M minus L, right? Well, first of all, since we are studying exclusively the portion of M below square root of 12, we will assume from now here that all sequences belong to this subshift here, right? And well, in general, you define you construct point in M minus L, it's somehow this construction is associated with non-semi-symmetric word of odd length. Well, we call a semi-symmetric word if the period sequence with period W it has the same orbit as the period sequence of period W transport, right? So if you take a non-semi-symmetric word of odd length, you can assume that the Markov value, the supreme along the orbit, it's attaining the 0 position. So to construct point in M minus L, you actually need two main ideas. You have to prove two properties. The first one is local uniqueness. That say basically the following: if you have a sequence with Markov value near to the Markov value of the period sequence, then your sequence must have a middle block around their 0 position, exactly the same with the same symbols of the periodic sequence, right? And we also need a property called self-replication. Well, since the words are not semi-symmetrically, the problem of gluing new letters on the left and on the right of the word are systematically different because the word is not palindrome, and actually a word is called semi-symmetric if it's palindrome or a concatenation of two palindromes. You can see it like this. So if the word is not palindrome, essentially the problem of gluing in the left and in the right are different problems. And since you have this kind of different gluing setting, you can hope to find an epsilon 2 positive, such that if you have a sequence with Markov value is less than the sequence, the Markov value of the period sequence plus epsilon 2, and you also have this middle block here, exactly the middle block of the periodic word, the word theta must self-replicate to the left. In the sense this word here should appear once more, this W here should appear once more to the left. And then if you apply this mechanism over and over again, you can conclude that the theta has this format, right? Well, if you put these two mechanisms together, you actually create an isolated point in the Lagrange spectra. Well, if you take a word non-semi-symmetric and they have the local uniqueness and self-replication, if you pick epsilon like the minimum of between two of them, you can see that the Lagrange spectra in this region here around the Markov value of the period sequence is only the Markov value of the period sequence. Indeed, if you take a period sequence here with Markov value in this interval by the local uniqueness and self-replication, the sequence should be like this one. And therefore, the period sequencing actually is equal to the period sequence with period W. So in that way, we show that the only Markov value of period sequence in this interval came from the period sequence of W. And since the Lagrange spectra coincide with the closure of the Markov value of period points, inside here we only can have this point here, right? Well, now that you have isolated the one point in the Lagrange spectra, you can hope to create a whole contour set inside this interval that you only have one point of the Lagrange spectra. The idea is the following. Since we are not forced to connect with this word here on the right with the W, well, this is the sequence that comes from after you apply the local uniqueness and self-replication. As you are not obliged to connect on the right with the W, you may expect to connect some new word here in such a way that subshift in such a way that after gluing this word, the Markov value of this sequence is not so big. So the Markov value still is attained in the 0 position here, and you can see that this whole sets here is inside of the Markov in this region here. And since this region doesn't have point of Lagrange, this whole C here is actually inside of Markov and Lagrange. Well, it's not so hard to see that this here, it's Bellipschitz. It's Bellipschitz to a Cantor set made by this word concatenate in a continued fraction. So you can estimate the half dimension of this portion of Markov of the M minus L by this half dimension of this Cantor set KB here, formed by this finite set of words. Right. So let me give some ideas of the proof. Well, before that, let me remind some results. There is a result from Bombieri that proved that if a sequence has Markov value is less than 3, so this sequence should be periodic with period 1, 2, or alpha beta, where alpha beta is admissible alphabet. What our admissible alphabet is? Well, if you take the word A como sendo 2, as being 2, and B as being 1, you can define the admissible alphabet as the vertices of this well-understood tree here, that you have a way to give new child for every vertex. So, well, doing an analysis of some of these admissible alphabets and of some process of renormalization, of some renormalization procedure, Eraso, Moreira, Gutierrez Rom, and Romana gives this estimative for the half dimension of M between the number 3 and 3 plus epsilon. They actually analyzed the combinatorial of words with Markov value near to 3. And after this analysis, they were able to do this estimative here. Well, from the proof of this result, of this previous result, we can see that the most of large finite words W that are subwords of some sequence theta with Markov value very close to T, very close to 3, can be written in an alphabet of this type, with a bunch of 1s and just 2 2s, right? For some large n. So in that scenario, you can always assume that the most of the word theta, the most of the sequence theta, has this format here, a bunch of 1s intercalate with 2 2s, right? And we also can assume that the Markov value of these words is attainable in the 0 position. Well, here the Markov value is attainable in the 0 position. It's the sum of these 2 continued fractions. And if you use the blue box here, this is the identity of continued fraction, you can change the upper sum in this 3 plus this difference of 2 continued fractions in a really well understood Cantor set that has this format here. So now we are in this situation. You have this Cantor set K, and you are projecting on K. Well, you have this Cantor set K, and you have the K times K, and we are projecting onto K minus K. Well, if you hope to prove some local uniqueness, you are looking for some situation like this in the B figure here, where different partitions of that fractal K times K project on different regions of the line. Right? Well, in order to do that, you can do that by steps. The first step of the construction of K times K times K times K. Sorry. Okay. Okay. If you take 2 points P1 and P2 and Q1 and Q2 here in this product, if they project sufficiently close, like this close here, if you use this asymptotic expression here for this fraction, discontinuous fraction here, that it's almost all one in the whole symbols. If you use this asymptotic expression here, you can check actually that E1 is equal to F1 and E minus 1 is equal to F minus 1. So in that scenario, you prove that all these rectangles here have disjoint projection in the first step, right? And well, the second step is the following. Well, we just prove here that these rectangles in the first step all of them have disjoint projections. Now you have to see what happened inside of each rectangle of this, right? Each one of these rectangles are subdivided in a bunch of new rectangles. The next step of the construction of the Cantor set, right? And well, the next step is given by this rectangle here. Then actually imagining of this bigger rectangle here by inverse branch of the Gauss map, for this inverse branch here. Well, since the first step has disjoint projection and the second step are image of this inverse branch, we hope to use the bounded distortion projection to also guarantee that this projection are disjoint as well. To suppose that there's 2 points P1 and P2 and Q1 and Q2, so that this both point project in the same point. So if you rewrite the previous equation like this one and use the bounded distortion property of this Cantor set K, here the bounded distortion property given here, you can rewrite this expression like this one here, right? Where mu is this relation between the negative and positive intervals of the construction. Well, and if you use again that asymptotic expression for discontinuous fraction, you can rewrite the previous equality in this format here. Well, so in some sense, you change the problem of local uniqueness to solve a exponential Lafontaine equation, where you have, you have the base here. It's a well-known number. Phi here is the golden ratio, right? It's an algebraic number. And if you use this paper from this theorem from Baker-Hultholz, that say something about the product of potential of algebraic numbers, we are able to prove that actually E2, in order to this equation here to be true, you need to have E2 equals to F2 and E minus 2 equals to F minus 2, right? Since the rectangle here, the rectangle in the first step, the previous step is distorted. Well, a rectangle be distorted, it's a rectangle like this one or like these other ones here, and they are stretched in more in one direction than the other, right? If you are in this condition, we can manage to prove that in the second step, E2 is equal to F2 and E minus 2 is equal to F minus 2. So we actually prove that if 2 points project 2 points in different rectangles in the second step projecting the same point, actually they came from the same rectangle, right? And you continue that argument inductively to prove self-application, to prove local uniqueness. Right. Well, but in our case, what kind of non-sample symmetric word do we pick? We pick, like, from the previous, based on the previous argument, we pick a large word of odd length with this format, a bunch of ones intercalate with two twos in the middle. Well, we have to put some conditions in order to get the whole thing work on. Well, you have to ask ST1, the first amount of ones here, should be n big enough and old. You have to ask S minus 1 to be that big in order the first step of the construction to be distorted. Well, if you have a bunch of ones, much more ones from one side, so this side which will be much more thinner than the other. And you have these two conditions here. Well, this one is needed to this word constructor appointing the Cantor set K. And this one is just to be sure that the Markov value of the periodic sequence is attained in the 0 position. So it's not so hard to see that this word is not symmetric, and the Markov value of the periodic sequence is attainable in the position 0. Well, for this sequence, actually for most of these words, each step of the construction is distorted, and they have disjoint project from all other combinatorials. So we prove like this the local uniqueness. And for every W in that conditions, we also prove the self-replication. So in this way, we can isolate the Markov value of the period in the Lagrange spectra. And we can also put this Cantor set here in the region between the Markov value of the period sequence and the Markov value of the period sequence plus some epsilon here. So you put a whole Cantor set, well understanding, we glue on the right a bunch of words from this really understand set here, and we use that this Cantor set here is Lipschitz to a Cantor set which is formed by this word in the using just this symbol, these two symbols to construct the Cantor set. So you use this Cantor set here to give that estimative before, and you can adjust the whole thing and taking n big enough in order to have this interval here inside of the interval 3 from 3 to 3 plus epsilon. Well, a final remark. I think I have time. I have 1 minute. Yeah. Well, as we've just seen, you have this below estimative here for the half of dimension of the difference set between Markov and Lagrange from 3 to 3 plus epsilon. And we also have this estimative here for the half of dimension of Markov in the same region. And more recently, Moreira, along with Villamil, proved an upper limitation for the half of dimension of this different set in the same region. So if you combine these 3 estimative together, we also can see that the half of dimension of this different set between 3 and 3 plus epsilon is essentially half of the dimension of the Markov set in the same region. Yeah, I think that's it.